Hello. Well, today I'm going to continue with this same example. I'm talking about solving the recurrence relation of an ODE. Here's a linear second order ODE with non-constant coefficients, that 1 plus x, or that x means it's non-constant coefficient of the ODE. It's homogeneous. All right, and we're finding a power series solution. Well, that y is this power series, and the CNs are the coefficients, the different meaning of the word coefficients of the power series. And we got this recurrence relation that C sub n plus 2 is n minus 2 over n plus 1 Cn, for n is 0, 1, 2, 3, 4, etc. An infinite number of equations. And in 3 of your webwork problems, the recurrence relation has this sort of form. All right. So let's answer the question of, let's find the general solution. Of the ODE. As a power series. So we're not going to get an exact solution here, we're going to get an approximate solution in a power series. All right, so let's just go through and see what the consequences of these are. So when n is 0, the first case, we get that C2 is negative 2 over 1 C0. When n is 1, we get C3 is 1 minus 2, negative 1 over, 1 plus 1 is 2, excuse me, 2 C1. When n is 2, we get C4 is 0 over 3 C2, because n is 2. When n is 4, we get C5, 4 minus 2 is, no, I want to do n is 3. When n is 3, what do we have? 3 minus 2 is 1. 3 plus 1 is 4, C3. When n is 4, colon, I get that C6 is 4 minus 2 is 2, over 4 plus 1 is 5, C4. When n is 5, colon, what do I get? C7 is 3 over 6 C5. Okay, now I wrote these all out without any further simplification. One thing is I want to make sure I did it all correctly, and you see as I write it out, it's kind of you can kind of see the pattern to make sure I did it right. First I have C0, 1, C2, 3, 4, good. The numerator is minus 2, minus 1, 0, 1, 2, 3. The denominator is 1, 2, 3, 4, 5, 6. Good. And then the thing on the left, C2, yeah. So it's nice to kind of write this all out, just to make sure you did it all correctly, because it's fraught with errors. In fact, watch me like a hawk. All right. So you notice that, first C0 and C1 are arbitrary. We've talked about that. Let's summarize this. Okay, let's summarize this. We got that C2 is negative 2C0. C1 is negative a half. Sorry, C3 is negative a half C1. C4 is 0, right? And in fact, notice that C6, since it's something times C4, that's 0. C8, that 0 is all of them, okay? All right, so now let's do the C odds. What is C5? C5 is a quarter C3. So it's first a quarter times C3. So that's 1 over 4 times 2 with a negative sign, C1, using what C3 is, right? And what is C5? C7 is 3/6 C5. But that's what C5 is, so I get a negative 3 over 6 times 4 times 2, C1. In fact, you probably can believe me, C9 is going to be negative 3 times 5 over 8 times 6 times 4 times 2 times C1. And C11 is minus 3 times 5 times 7 over 10 times 8 times 6 times 4 times 2, all times C1. So the result, as happens in all of these cases, is all the even C evens are something times C0, a lot of them times 0 times C0, and all the C odds are something times C1. All right. And that doesn't always happen. What does happen in general is that C anything, like in general, C9 will be something times C0 plus something times C1. But for special symmetry of these problems, I'll probably talk about later, I might not. For all of these, all of the odds, C sub odds, depend only on C1, and all the C sub evens depend only on C0. All right. So let's use that to find our solution. We want to find our general solution. Well, our general solution is, y is C0 plus C1x plus C2x squared plus C3x cubed plus ... In this case, it's going to be C0 plus C1x minus 2C0x squared. All right, and then what's the C3? Minus a half C1x cubed, that's C3, plus 0 times x to the 4. And then C5 is minus 1 over 4 times 2 C1x cubed, all right, plus 0 times x6. And then let's just do one more, the C5 we have. Oops, that was a C5. We'll do the C. That was a C5. We'll do we'll do x to the 7 minus. Oops, we already got the minus 3 over 6 times 4 times 2 times C1 x to the 7 plus ... All right. So what I want to do here is I want to separate all the things that have a C0 in them and the things that have a C1 in them. And I can write the solution as y is C0 times 1 minus 2x squared, period. Just close it up, right? That is actually an exact solution because it's plus 0 times x to the 4th, plus 0 times x to the 6th, plus 0. All the rest of the terms in the Taylor series for this solution are 0. And then I have plus C1. What's in front of C1? Well, it starts with x. It's got to start, this guy always starts with a 1, that guy always starts with an x. And then the cubic term is going to be minus a half x cubed, then minus 1 over 4 times 2x to the 5th, minus 3 over 6 times 4 times 2, x to the 7th, plus dot, dot, dot. All right. So I have found two linearly independent solutions. And it would be nice if we called that y sub the zero of the solution in the first, but that's not the way we usually do it. This is, and it's always going to be of the form y is c naught times y1 of x plus c2 times y2 of x. Sorry, plus c1. Right? When I apply the recurrence relationship, I'm always going to get y is the arbitrary c0 times something, I'm calling that y1 of x, plus the arbitrary c1 times something, I'm calling that y2 of x, right? And in this case, y1 of x is 1 minus 2x squared, an exact solution. In fact, that's one of the great things about power series methods is they allow us to find, in many cases, exact polynomial solutions. And then the second solution is linearly independent from the first one, is the thing in front of C1, that's going to be x minus a half x cubed minus 1 over 4 times 2x to the 5th minus 3 over 6 times 4 times 2x to the 7th plus dot, dot, dot. And then that one will keep on going. So, so we don't have an exact solution here. We just get a series solution, but when x is small, it's a very accurate solution. Okay, so some of your webwork problems ask you for these two functions. The function that starts out with 1 and the other function that starts out with x. And there are various different variations on this theme. All right. So let me just circle this solution. The question was to find the general solution of the ODE, and here I've done it. That is the general solution of this ODE, not written with the power series. So I got one exact solution, which is really cool, but one thing that just has a power series here. Sometimes it's a little bit harder to see the pattern than others. We might be able to see the pattern, and you have one problem, I think it's 5, where you actually do have to recognize the pattern. I will maybe talk about that more, but maybe I won't. In case I don't talk about it more, I want to give you a little hint. A little hint. If I have something like 2 times 4 times 6 times 8 times 10, this is equal to 2 times 1 times 2 times 3 times 4 times 5, right? Oops. This is going to be 1, 2, 3, 4, 5. This is going to be 2 to the 5th. That's 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4, 2 times 5, right? There's a 2 to the 5th here. So this is 2 to the 5th times 5 factorial. Right? And similarly, if I go 2 times 4 times 6 times 8 times 10 times dot, 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 all the way up to 2n, so there's going to be, that's the first term, second term, there's n factors, I get this thing here is 2 to the n times n factorial, right? Because it's 2 times 1 times 2 times 2 times 2 times 3, dot, 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 all the way times 2 times n. So I think there's n factors of 2, and then there's also factors 1 times 2 times 3 times 4 up to n. Okay, so a technique like this is going to be very helpful in your problem 5. All right, so All right, so I hope that you get a feeling for this. I want to just mention one more thing, that when we were looking at the curriculum and we were wondering if we should maybe take out this topic out of Math 239, take out series solutions, the mechanical engineers said, no, you've got to do it. We use series solutions a lot. And so this is an important thing in applications. One of the most important, as we said, is it's a way to find exact polynomial solutions that would be really hard to find any other way. And another thing is something like boundary layers and in fluid mechanics and a lot of problems, these power series solutions, even when they're not exact, but like this, are very useful in physics and engineering applications. All right, goodbye.